In this video, we're going to learn how to determine the formal charge on an atom in a compound. So formal charge is a great way that we use to determine whether or not a structure is likely to be stable for a given arrangement of atoms. And we'll talk more about how formal charge impacts stability in class. For now, our goal is just to learn how to determine the formal charge on an atom. So essentially what the formal charge is doing is comparing the arrangement of electrons around an atom in a compound to kind of the typical or preferred electron arrangement for that element. So essentially what it's asking, if all of our bonds were split in half, how many electrons would the atom have? And how does this compare to its usual number of valence electrons? If it has more electrons in the compound than is normal, the formal charge is going to be negative. Since it has extra electrons, it has extra negative charge. If it is the same as its usual number of valence electrons, the formal charge is equal to 0. And if it has fewer electrons around it in the compound than is typical, the formal charge is positive since it's missing some negative charge. So the sum of all of your formal charges in the compound should be equal to the charge on the molecule or ion. So we're going to look at a couple of examples. First, I would like you to pause here for a minute and try to draw Lewis structures for these three compounds. So first up, we have the cyanide ion Cn-. Since it's only two atoms, we don't really have a central atom, so we don't really need to worry about determining our central atom. But what we should do is figure out the total number of valence electrons that are going to be represented in this structure. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. And that negative charge gives us 1 extra electron. So we have a total of 10 electrons that we need to represent in this structure. So if we start out by connecting our atoms by a single bond, that takes care of 2 of our valence electrons. We have 8 more that we need to place. So if we place these, it doesn't really matter how in this case. And if we fill up the nitrogen, we'll still have 2 left that we would need to put on the carbon. Now, the structure is not finished because our carbon has an incomplete octet. We don't have any more electrons to place, so we can't just put additional lone pairs on it. We already have 2, 4, 6, 8, 10, which is the correct number of electrons, so we can't add any more, which means that what we need to do is increase the number of electrons that are shared. So if we take one of these lone pairs off of nitrogen and create a double bond, that gets us a little bit closer, but we're still not quite there. This carbon has 2 electrons from its lone pair, 2 from this bond and 2 from this bond for a total of 6, but we're looking for 8 in order for it to have a complete octet. So we need to increase the number of shared electrons even more by moving another one of nitrogen's lone pairs to create a triple bond. Now, nitrogen still has a filled octet. It has 2 electrons in this lone pair, plus 2 from each of these 3 bonds for a total of 8, and carbon has the same. It has 2 from this lone pair, plus 2 from each of these 3 bonds for a total of 8. So that is our Lewis structure for the Cn- ion. For O3, we have 3 atoms of the same element. So 1 oxygen in the middle with 2 on both sides. Each oxygen atom brings 6 valence electrons with it. So we have a total of 18 electrons that we need to place. So we always want to fill up the octets of our peripheral atoms first before we add electrons to the central atom. So if we do that, currently this oxygen has 2 electrons, which means it needs 6 more. So if we give it 3 lone pairs, that gives the oxygen on the left a filled octet. We can do the same thing for the oxygen on the right. So that one now has a filled octet as well. And that just leaves the oxygen in the middle, but we want to check how many electrons we have left. So at this point, we have drawn 2, 4, 6, 8, 10, 12, 14, 16. So we currently have 16 in our structure and we're looking for 18, which means we only have 2 electrons left to place. They have to go on the central atom, but we can't put any more in, even though that oxygen doesn't have a filled octet. So this is another case where we're out of electrons, but we haven't filled all of our valence shells. So we need to take one of our pairs of electrons off of a peripheral oxygen and use it to create another bond. This oxygen on the left here still has a filled octet, has 4 electrons from its 2 lone pairs plus 4 electrons from the double bond. So that's still good. And now our central atom has 2 from this lone pair, 4 from this double bond, 2 from this single bond, for the total of 8 that we're looking for. And the one on the right is fine. As we saw earlier when we were filling it up, we started with 2 from this single bond and added 6 more in the form of 3 lone pairs. So this is our Lewis structure for ozone for O3. And then the last one, IF4 plus, iodine gives us 7 valence electrons. Each fluorine also brings 7, so we'll do 4 times 7. And then that positive charge means we lost an electron. So 4 times 7 is 28, plus 7 is 35, minus 1 is 34 electrons that we need to represent in this structure. So our central atom will be the iodine, since it is both one of a kind and less electronegative than fluorine. We can put the iodine in the middle with the 4 fluorines around it, connected by single bonds. Fill up the valence shells of all of our fluorine atoms. And at this point, we have placed 32 electrons in our structure. We have 8 in these 4 single bonds, and then we have 6 in the form of lone pairs on each of our fluorines. So that means we have 2 electrons left to place. The only place that we can put them is on the iodine, is on the central atom. So in this case, our central atom has what's known as an expanded octet, which can happen for any elements in period 3 and below, so periods 3 through 7 on the periodic table, because those atoms are large enough to accommodate those extra electrons around them. So iodine is in period 5. So it is plenty big enough to accommodate that extra pair of electrons. So that's not a problem here. So talking about formal charge, we assign formal charges by thinking about what happens if I split my bonds in half. So we know that each bond contains 2 electrons. So if I imagine chopping my bonds in half here, my electrons get split apart. So each bond contains 1 electron. When I split it down the middle, sorry, each bond contains 2 electrons. When I split it down the middle, each atom gets 1 of those 2 electrons. So in the triple bond, we have 3 pairs being shared. So each atom ends up with 3 electrons out of the 6 that they were sharing. They also have total ownership over their lone pairs. So in this structure, carbon has 5 electrons around it. And nitrogen also has 5 electrons around it. Now we need to think about the normal amount of valence electrons that these atoms have. How many do they bring to the party? We already looked at over here, that carbon typically has 4. Based on where it is in the periodic table. So compared to its normal number of valence electrons in the cyanide ion, carbon has an extra. So there's 1 extra electron on the carbon in the cyanide ion, which means that its formal charge is -1. It has an extra electron, it has an extra negative charge around it. So we indicate that by putting a little negative sign near the carbon, and you will often see the formal charge circled. It doesn't always have to be, it's kind of a matter of preference and discipline. Organic chemists tend to circle it, other chemists frequently don't, in my experience anyways, but I will usually circle it just to make it more obvious. Otherwise, it's really easy, especially for a negative sign, to just look like a stray mark on the paper, whereas the negative with the circle just kind of makes it more intentional. So I will always circle it to call it out. You don't necessarily have to. For the nitrogen, it has 5 electrons around it as well, and 5 is the norm for nitrogen. So this is the same as its normal amount or its typical amount. So our formal charge is 0. The formal charge is essentially the difference in the number of electrons in this compound versus its typical number of valence electrons. So if they're the same, there's no difference, so our formal charge is 0. When the formal charge is 0, we don't write anything near the ion, or sorry, near the atom. If the formal charge is not 0, it must be indicated. Otherwise, your structure is not actually complete. So that's the general gist for how we assign formal charges. If you have extras, it's negative. If you're missing some, it's positive. And how many extra you have is the value of the charge. We had 1 extra, so it was -1. If there were 2 extra, it would be -2, so on and so forth. So pause here and take a few minutes to try to assign formal charges to every atom in the other 2 compounds that we drew structures for. So in ozone, we once again want to think about splitting our bonds down the middle, and what do we get? So if we split our bonds in half, we have a double bond on the left, so 2 electrons go to each of those atoms. We have a single bond on the right, so 1 electron goes to each of those atoms. So the first oxygen on the left gets 2 electrons from the bond, and it has 4 additional electrons around it from its lone pairs for a total of 6 electrons, which is the same as its normal amount. Oxygen atoms typically bring 6 valence electrons. So this is same as normal or typical. So our formal charge is equal to 0. For the one in the middle, we have 2 from the double bond, 1 from the single bond, plus these 2 from the lone pair for a total of 5 electrons. This, compared to the 6 it likes, is missing 1 electron. If we have 1 fewer negative charge, our formal charge is going to be +1. So we would indicate that with a little plus sign near that central oxygen. And again, I'm circling it for clarity, matter of preference for the most part there. Then the oxygen on the right is getting 1 electron from the single bond, plus all 6 of these electrons from its lone pairs, for a total of 7 electrons around it in this particular compound, which is 1 electron extra. Extra electrons means negative formal charge. 1 extra means -1 formal charge. So this guy has a minus. It doesn't matter exactly where you place that formal charge, above, below, beside, doesn't matter, just close to that particular atom. So it's clear that it's associated with that one and not a different one. And then our last example was the IF4+. So if we once again imagine splitting all of our bonds in half here, they're all single bonds. So 1 electron goes to each side. And then our fluorines each have 3 lone pairs. They all look pretty much the same, so they're all going to have the same formal charge. All of our fluorine atoms are involved in 1 single bond, and they have 3 lone pairs, which gives them a total of 7 electrons, which is the same as their normal number of valence electrons. So the formal charge of all of the fluorine atoms in this ion is equal to 0. Now the iodine got 1 electron from each of these 4 bonds, plus it has 2 from its lone pair, for a total of 6 electrons, which is 1 less than the 7 that is typical. So its formal charge is +1. So we would put a little plus sign in near that iodine somewhere. So one other thing to notice that can be helpful when you're checking your formal charges and checking your structures for numbers of electrons is this idea that the sum of all of your formal charges should equal the charge on the molecule or ion. So in the case of Cn-, we have a -1 charge. That means the sum of all of my formal charges should be -1. And I had 0 and -1. 0 plus -1 is -1, so that works. If the sum of your formal charges comes out correct, that means you have the right number of electrons. If the sum of your formal charges is wrong, that means you don't have the proper number of electrons represented in your structure. So for the next one, our charge total was 0 here. So that means our formal charges need to add to 0. We have a +1 and we have a -1. So those do add to 0. And then in the last one, we had a +1 overall, and we had a +1 on our iodine, along with a bunch of zeros on all of our fluorines.